Good afternoon, students. Today we are going to see the topic Introduction to Vectors. So in electromagnetic field theory, it directly deals with electric field. Whereas in circuit theory, we have voltage and current. Voltage contributes the electric field as well as current contributes the magnetic field. So in general, electromagnetic field theory problems involve three space variables along with the time variable, and hence solution tends to become correspondingly complex. Therefore, we are going for vector analysis. So in vector, any physical quantity may be scalar quantity or vector quantity. A scalar quantity is specified by magnitude only, whereas vector quantity requires both magnitude as well as direction. Generally, field is defined as it is a function that specifies a particular quantity everywhere in a region. Generally, field can be classified into scalar field and vector field. Scalar field, here the scalar is a quantity that has only magnitude. For example, mass, distance, temperature, entropy, electric potential, population are scalars. Similarly, vector, we have both magnitude and direction. Okay. Vector analysis. Those quantities which can be represented by magnitude and directions. So we have following types of vectors: zero vector, unit vector, then position vector, co-initial vector, like and unlike vectors, co-planar vector, co-linear vector, equal vector, and then displacement vector. And also we have negative of a vector. So in general, by using head and tail notation, generally a vector has two components, magnitude as well as direction. Any vector can be represented by magnitude as well as direction. For example, we have linear momentum, acceleration, displacement, angular velocity, force, electric fields are some of the examples for vector quantity. A vector which has a magnitude of unit length is called unit vector. Suppose if x vector is a vector having magnitude x, then unit vector is denoted by x cap in the direction of the vector x vector and has the magnitude equal to 1. Suppose any vector can be represented by magnitude as well as direction. So for unit vector, here the magnitude is equal to 1. So generally unit vector can be useful to indicate the direction of the vector quantity. Suppose in a Cartesian coordinate system, we have x, y, z. So we have three axes. Then axis along x we have direction is I vector. Suppose along y axis we have j vector. Then z axis we have k vector. So in general, a vector can be represented by x vector equal to magnitude of x into x cap. So that magnitude of x denotes scalar quantity, and x cap is the direction. From that, x cap equal to that given vector x vector divided by x, modulus of x, that is magnitude. So in general, we are representing the vector a vector equal to x comma y comma z using brackets. Similarly, a vector can be represented by x I cap plus y j cap plus z k cap. Okay. Then next one is position vector. Suppose we are taking OAS taken as reference origin, OAS taken as origin, then we have object, it is denoted by a point P, P of x comma y comma z. Then the vector, suppose the vector O2P, O2P is denoted by OB vector, is called as position vector of that point. Okay, position vector simply denotes the position or location of that given point. So that point may be available in Cartesian coordinate system or cylindrical coordinate system. Okay. Then properties of vectors. Suppose A, B, C are vectors and small m, small n are scalars. Then we have A plus B equal to B plus A. It will obey the commutative law. Okay. Similarly, A plus B plus C equal to, we can write A plus B plus C. It will obey associative law. Similarly, in subtraction, A minus B equal to, I can write A plus within bracket minus B. Okay. Then for multiplication, we have multiplication by scalar and then multiplication by vectors. Suppose here the m is the scalar, m into a equal to a into m, commutative law. Then m into within bracket na equal to n into ma, associative law. Then vectors m plus n scalar into a vector equal to, we can multiply m into a plus n into a. It obeys the distributive law. Then m into a plus b equal to m into a plus m into b. Again it obeys the distributive law. A position vector is represented graphically by a directed line segment. So a unit vector is a vector of unit magnitude equal to 1 and directed along with that vector. Okay. So a cap is a unit vector along the direction of A. Okay. So in general, a unit vector is a vector with a magnitude of 1 unit. So any vector can be represented as a scalar multiple of its unit vector. So in generally, a vector, so here we have origin point is A, then point A having the another point. So here OA is our vector. So OA is our vector, magnitude is magnitude of OA. Then we have unit vector A vector OA. From that unit vector A vector OA equal to that vector divided by magnitude. Okay. So similarly we can represent like this. So along the x-axis we have direction ax cap, along the y-axis we have ay cap, along the z-axis we have az cap. Okay. Similarly, we can point out the p of xyz in the Cartesian system. We can represent like this. Then we have, suppose we have 2 points. Point 1 is P having x1, y1, z1. Then another point in Cartesian system, xyz plane, we have Q of x2, y2, z2. Okay, so I can write the P vector equal to x1 a cap ax vector plus y1 ay vector plus z1 az vector. Similarly, second vector q bar equal to x2 ax cap plus y2 ay cap plus z2 az cap. Then we have distance between these 2 points is denoted by PQ vector equal to Q minus P vector. Q vector minus P vector. So we can write x2 minus x1 Ax cap. So in the y direction, y axis, we have 2 points, y2 minus y1 Ay cap. Along the z axis, we have z2 minus z1 Az cap. Therefore, we can write PQ bar modulus equal to magnitude equal to square root of x2 minus x1 the whole squared plus y2 minus y1 the whole squared plus z2 minus z1 the whole squared. Therefore, P vector equal to PQ, that is distance equal to that vector PQ vector divided by magnitude of that vector. Okay. So therefore, in general, a graphical representation of A vector A has, we have 2 components, that is magnitude as well as direction. Magnitude is A and A cap is the direction. So we can write it as A cap A equal to A vector divided by modulus of A. Okay. Then for multiplication of vectors, we have 2 components. One is dot product, another one is cross product. So here we have A vector, then B vector. So in the dot product, we have A dot B vector equal to, we have the general formula, A vector AB cos theta, okay. So here theta between 0 to pi, okay. So basically it is a scalar quantity. Basically it is a AB cos theta is a scalar quantity. So generally dot product gives the scalar quantity. Whereas A cross B vector, A vector cross B vector equal to C. Here we have AB sin theta. So here the theta is the angle between A and B, that is 0 to pi. And n cap is the unit vector perpendicular to plane of A and B, directed such that ABC form the right candidate system of vectors. So here A cross B equal to minus B cross A. Whereas in dot product, A dot B equal to B dot A. So here we have scalar quantity. Here we have vector quantity. Therefore, A vector cross B vector equal to minus B vector cross A vector. Similarly, A vector cross B plus C vector equal to A cross B plus A cross C. So in this video we have seen the basic definitions of vectors. Thank you.